Ever have one of those moments? You know, that little spark where something just clicks and you think, hang on, that changes everything.
Uh-huh.
Well, that's what we're chasing today. We're doing a deep dive, a shortcut really, into an energy idea that's, well, potentially revolutionary. It's been hovering right on the edge of science fiction for years.
We are indeed. We're looking at zero-point energy, or ZPE. It's this really tantalizing idea. The possibility is actually drawing power from the fundamental fabric of space itself.
From space. Which, we normally think of as totally empty. Like, remember those science class experiments? You pump all the air out of a jar.
Right, the classical vacuum, no air, no matter, just nothing left inside.
Exactly. Nothing.
But that's where quantum mechanics really throws a curveball. The quantum view is completely different. This vacuum isn't empty or static at all. It's more like a seething, energetic foam at the tiniest scales imaginable.
The seething foam. How does emptiness manage to seethe?
Well, it comes down to Heisenberg's uncertainty principle. You know, the idea that you can't perfectly know certain pairs of properties, like a particle's exact position and momentum, at the same time.
Right, there's always some fuzziness at the quantum level.
Exactly. And that fundamental uncertainty actually allows for these tiny, fleeting fluctuations in energy. It lets virtual particles, think electron-positron pairs, for example, pop into existence and then vanish almost instantly.
Okay, wait, so particles just appear
Yeah.
out of nowhere
Yeah.
and then disappear.
For incredibly short moments, yes. But their constant appearance and disappearance creates this underlying background energy, and that is the zero-point energy.
So it's the baseline energy of space itself, even if you could cool it down to absolute zero.
Precisely. It permeates everything everywhere, and the amount of energy potentially locked up in there, well, the estimates are just staggering. Some theoretical calculations suggest a single cubic centimeter of vacuum might hold enough energy to boil every ocean on Earth.
Okay, hold on. Boil all the oceans from what looks like nothing.
It's a theoretical upper limit, of course, and a mind-boggling one, but it gives you a sense of the sheer scale we might be talking about.
Wow. Even if it's a fraction of that, the implications are enormous. We're talking clean energy.
Completely clean. No greenhouse gases, no pollutants, and it's omnipresent, available literally anywhere in the universe. No more fighting over geographical resources.
Which sounds almost too good to be true.
Yeah.
So what's the catch? Why haven't we tapped into this already if it's been theorized for decades?
Well, there's significant scientific and technological hurdles. Huge ones. It's been fringe science for a long time for good reason.
But something's changing now. Recent breakthroughs are making it seem more tangible.
Yes, exactly. Advances in quantum field theory, combined with really exciting developments in nanotechnology, material science, we're starting to get the tools, and perhaps the understanding, to interact with this quantum foam in ways we couldn't before. Things like metamaterials engineered at the nanoscale.
So the mission for us today, for you listening, is to really unpack this, understand the basics, explore these new tech advancements, and think about what harnessing ZPE could actually mean for, well, everything.
Let's do it. Where should we start? Maybe digging a bit deeper into that quantum vacuum versus the old classical idea.
Good idea. You mentioned the seething foam. Can you elaborate on that contrast? The classical airtight container versus this quantum dance floor.
Absolutely. So classical physics, vacuum equals void. Total absence, zero energy. Simple, right?
Seems logical.
But the quantum view, driven by that uncertainty principle, says nope. Even with no real particles, you have these energy fluctuations, these virtual particles constantly winking in and out of existence. It's inherently energetic.
It's the ground state, the baseline energy level of all the quantum fields filling space.
You've got it. It's the lowest possible energy state, but that lowest state isn't zero energy. It's this 0-point value.
And these virtual particles, these electron-positron pairs, they're real enough to contribute to this energy, even if they vanish immediately. It still feels a bit like, well, magic.
It definitely challenges our everyday intuition. Their existence is incredibly brief, dictated by the energy-time uncertainty relation. More energy means an even shorter lifespan. But collectively, across all possible frequencies, they create this persistent background energy field.
Okay, I think I'm starting to grasp the what.
Okay.
But the how do we possibly get usable energy from this ephemeral background buzz? What are the big obstacles?
The absolute core challenge is figuring out how to extract net energy. How do you dip into this sea of fluctuations and pull out more energy than you put in without violating fundamental laws like the conservation of energy? It's an incredibly delicate balance.
Right, you can't just stick a pipe into the vacuum and expect energy to flow out.
Not quite. The vacuum is generally considered to be in its lowest energy state, its ground state. Extracting energy usually means pushing something to an even lower state, which is tricky when you're already at the bottom. However, there are phenomena that show ZPE has real, measurable effects.
Like the Casimir effect, I've heard of that.
Exactly. The Casimir effect is probably the most famous, experimentally verified manifestation of ZPE. You take two perfectly smooth, uncharged conducting plates and bring them incredibly close together in a vacuum.
And a force pulls them together.
Precisely. An attractive force. The space between the plates restricts which wavelengths of virtual photons can exist there, compared to the infinite space outside. It's like the plates create boundary conditions.
So there's less ZPE pressure between the plates than outside.
Effectively, yes. The ZPE density is lower between them, leading to an inward pressure from the outside vacuum, pushing the plates together. It's physical proof that this vacuum energy isn't just theoretical.
That's fascinating. It makes it feel much more real.
It absolutely does. And what's really interesting now is that companies are actively working on this. For instance, Jovian Core. They're specifically looking into Casimir-based technologies. Their goal is to actually try and convert these vacuum fluctuations, this Casimir pressure, into usable electrical power.
Really? So they're trying to build a device based on that effect.
That's the aim. It's definitely early days, still deep in research and development, I'd imagine, but it represents a concrete engineering approach to harnessing ZPE.
Okay, so Jovian Core is tackling the Casimir effect. That's one pathway. What other key steps or areas are researchers looking at to truly, crack this nut?
Well, another huge area is what you might call preparing the quantum vacuum, inducing some kind of order.
Order in that chaotic foam.
Yeah, think about it. Trying to get energy from random chaotic fluctuations is incredibly inefficient. It's like trying to fill a tiny cup from a raging ocean wave by wave.
Okay, I see. You want something more coordinated.
Exactly. The buzzword is coherence. Getting the quantum fluctuations or components of the vacuum state to act more in unison, more predictably. Like how a laser creates coherent light compared to the jumble of frequencies from a regular light bulb.
Ah, the laser analogy helps.
Yeah.
So achieving coherence is seen as essential for efficient energy extraction.
It's widely believed to be, yes. And this is where some other players come in. Skywise AI, for example, is taking a really interesting approach using artificial intelligence.
AI, how does that fit in?
They're using AI to design and model incredibly complex nanoscale structures, fractal energy collectors.
Fractal, like those self-repeating patterns.
Precisely. Fractals have this unique property of interacting with a wide range of frequencies or scales because of their repeating geometry. Skywise AI is essentially designing nanoscale antennas with these fractal shapes.
Antennas for ZPE.
Kind of, yeah. The idea is that these precisely structured materials might resonate with a broader spectrum of the ZP frequencies, allowing for more effective absorption or interaction. They're trying to tune the material itself to the vacuum energy.
Wow. Nanoscale fractal antennas designed by AI. That sounds incredibly advanced.
It is. And then you have another company, 0 Point Energy Ltd., taking a different tack altogether. They're focusing on waste heat.
Waste heat. How does that connect to ZPE?
Their approach involves developing highly efficient axial engines designed to operate near absolute zero temperatures. The hypothesis seems to be that by creating these ultra-low energy environments, possibly by repurposing waste heat to drive the cooling process, they can somehow enhance the conditions for ZPE extraction, maybe making the vacuum state easier to manipulate or access in that extreme cold.
So manipulating extreme cold using waste heat to maybe tap into ZPE is quite a different angle.
It is. So you see, we have Jovian Core focusing on the Casimir effect, Skywise AI on AI-designed fractal resonators, and 0 Point Energy Ltd. Exploring this low-temperature waste heat repurposing angle with axial engines. 3 distinct approaches.
It really highlights that nobody's cracked it yet, but there's serious, diverse innovation happening. It's not just one single idea anymore.
Exactly. It signals a shift. ZPE is moving from being purely a physicist's thought experiment towards something engineers are actively trying to build systems around.
And for you listening, this is maybe that aha moment starting to form. It's not just theory now. There are companies, actual research efforts trying to make this real. And, for those interested in cutting-edge tech, these early-stage companies, they represent potential investment opportunities down the line. Right. Though obviously high risk.
Definitely high risk, like any truly disruptive technology in its infancy. But yes, the fact that venture capital and dedicated R&D efforts are flowing into companies with names like 0 Point Energy Ltd. and Jovian Corp Focusing on these specific ZPE mechanisms, it tells you something significant is potentially brewing.
Okay, so let's assume one of these approaches, or maybe a combination, starts showing real promise. Let's talk about the actual process. We've mentioned coherence, fractal collectors. What else is needed? How do you go from interacting with the vacuum to actually, say, powering a light bulb?
Right, good question. Besides preparing the vacuum, achieving coherence, and having some mechanism to interact with it, like fractal collectors or Casimir plates, you need a few more critical pieces. One is incredibly precise monitoring and control,
Why is that so crucial?
because we're dealing with quantum systems, which are notoriously sensitive. You need ultra-sensitive quantum sensors to monitor the state of the vacuum and the energy extraction process in real time. Think of it like a tightrope walker constantly making tiny adjustments to stay balanced. These sensors would provide the feedback needed to keep the system stable and efficient.
So quantum sensors acting as the eyes and ears, making sure everything stays on track.
Exactly. They detect subtle changes, allowing the system to adapt and maintain coherence, preventing it from collapsing back into chaos, which is called decoherence.
Okay, coherence, collectors, sensors. Then what?
Yeah.
You've captured this raw quantum energy.
Yeah.
How do you make it useful?
Energy conversion. That raw quantum energy isn't likely to be directly usable as, say, electricity. You need to convert it. And this is where another fascinating area of physics comes in: superconductivity.
Superconductivity. Zero electrical resistance, right, usually at very low temperatures.
That's the one. Superconducting materials could be absolutely crucial. Once you've extracted the energy, you need to transfer it and convert it with maximum efficiency. Superconductors allow electrical current to flow with zero loss. Think of it like a perfectly frictionless water wheel connected to a generator, no energy wasted in the transfer.
So ZPE extraction might inherently require these ultra-cold, superconducting environments, potentially linking back to what zero-point energy LTD is exploring.
It's certainly a strong possibility, yes. The efficiency gains from superconductivity could be essential for making the whole process viable, ensuring the energy harvested isn't lost during conversion and transmission.
Okay, this is starting to sound like a complex, interconnected system. Coherence, collection, sensing, conversion. Is there a name for this kind of integrated system?
Well, some of the research, particularly related to the fractal resonance ideas like Skywise AI is pursuing, talks about concepts like ZYHOT, zero-point energy harvesting, and optimization technology.
ZYHOT.
Okay. It's important to understand ZYHOT wouldn't be a single gadget. It's more like an entire system, an orchestra of components working together. You'd have the coherence engine, maybe using carefully tuned electromagnetic fields or those specialized metamaterials to gently nudge the vacuum into that ordered state, like a shepherd guiding sheep.
Okay.
Then the fractal collectors or other resonance structures do their work, interacting with the coherent vacuum. The quantum sensors, as we said, are the eyes, constantly monitoring, feeding back data. The superconducting circuits then whisk the energy away for conversion into electricity, probably.
Like a conductor leading the symphony. Each part has to be perfectly timed and tuned.
That's a great analogy. And there's one more piece. Maintaining stability over time. These systems might need a sort of controlled reset process periodically.
A reset.
To ensure long-term stability and efficiency. You might need to briefly halt extraction, allow the local vacuum state to relax, recalibrate the sensors, maybe fine-tune the collectors. Think of a farmer letting a field lie fallow for a season to restore its nutrients.
Makes sense. So it's a cycle. Prepare, extract, sense, convoke, maybe reset, and repeat.
That seems to be the conceptual framework emerging, yes. A continuous, actively managed cycle.
This brings up another question. If you're extracting energy, even if it's converted efficiently,
Right.
where do you store it? Our current batteries are based on chemistry. Would they even work for potentially vast amounts of quantum-derived energy?
That's a critical point, and it leads to another potentially revolutionary technology often discussed alongside ZPE. Quantum battery.
Quantum batteries. How would they differ from, say, the lithium-ion battery in my phone?
Fundamentally different. Conventional batteries store energy via chemical reactions moving ions around. Quantum batteries, theoretically, would store energy directly in the quantum states of matter. Think of atoms or molecules being precisely held in excited energy states.
So energy stored not in chemical bonds, but in the quantum energy levels themselves.
Exactly. You could potentially store energy much more densely and release it much faster and more efficiently. Imagine a vast reservoir where energy is held in discrete quantum containers that can be opened and closed with incredible precision.
How would you build such a thing?
Again, advanced materials and superconductivity likely play a role. Researchers are exploring using superconducting materials to create quantum wells nanoscale structures that can trap and hold quantum states and thus energy in a controlled way.
So the development of ZPE might actually require the parallel development of quantum batteries for it to be truly useful on a large scale.
It seems very likely. Having a source of potentially limitless energy is one thing. Being able to store and deploy it effectively when and where needed is another. Scalable quantum batteries could be the missing link to realizing ZP's full potential.
Okay, let's step back for a moment. Assume we overcome these immense challenges. We figure out coherence, extraction, conversion, storage. What does a world powered by ZPE actually look like? What are the revolutionary impacts we're hinting at?
Oh, the potential impacts are, well, they're almost hard to fully comprehend. It changes fundamentally everything related to energy.
Start with the obvious, the energy landscape itself.
It's complete transformation. You'd move away almost entirely from fossil fuels, obviously. But even beyond that, think decentralized power. Clean, abundant energy available anywhere. Energy scarcity could become a memory. Power grids might look completely different, perhaps smaller, localized, self-sufficient hubs.
What about transportation?
ZPE-powered vehicles, perhaps using those quantum batteries.
Mhm.
Imagine cars, trucks, ships, maybe even planes, running on clean vacuum energy. No emissions. The entire automotive and transport industry transformed.
Urban infrastructure, cities.
Buildings or even entire city blocks could potentially become energy self-sufficient. Increase resilience against grid failures. Maybe power lines become less necessary in some areas.
Industry must change drastically, too.
Absolutely. Any energy-intensive industry, manufacturing, materials processing data centers could dramatically reduce its environmental footprint. It
Yeah.
could unlock new industrial processes that are currently too energy expensive.
And thinking even further ahead, quantum technologies.
That's a huge one. Quantum computers are incredibly powerful, but also potentially very energy hungry. ZPE could provide the clean, stable power needed to run large-scale quantum computers, accelerating breakthroughs in medicine, materials science, AI, logistics, you name it.
Even communication.
Potentially powering ultra-fast, ultra-secure quantum communication networks, the synergies are immense.
It sounds like a complete paradigm shift. What about globally? Sustainability, equity.
This is where the potential is truly profound. Firstly, climate change, ZPE, offers a direct path away from fossil fuels, potentially the ultimate tool for decarbonization.
A game changer for the planet.
Absolutely. But also think about global equity. Access to cheap, abundant energy could lift communities out of poverty worldwide. Imagine remote villages having access to reliable power for the first time, enabling education, healthcare, economic development.
It could fundamentally reshape geopolitics, too, right?
Yeah.
Less dependence on oil-rich nations, perhaps.
Potentially, yes. It could shift the focus from competition over finite resources to perhaps collaboration on harnessing this universal energy source. It could be a powerful force for global cooperation if managed wisely.
If managed wisely seems like a crucial caveat there, because with any technology this potentially powerful, there have to be downsides, major challenges, ethical considerations.
Oh, absolutely. We've painted a rosy picture of the potential, but the path is fraught with difficulties and dangers. We shouldn't underestimate them.
Let's talk about the technical and theoretical roadblocks first.
Yeah.
What are the big remaining scientific mountains to climb?
Well, maintaining that quantum coherence we talked about on a large scale and for extended periods, that's incredibly difficult. Quantum states are fragile. It's like trying to build a house of cards in a hurricane.
Decoherence is the enemy.
Always. Then there are the materials science challenges. We might need materials that can operate under extreme conditions, maybe at those ultra-low temperatures for superconductivity, or withstand unique stresses from interacting with the vacuum. Developing and manufacturing those materials reliably and affordably is a huge task.
And fundamentally, do we even fully understand the quantum vacuum yet?
That's the bedrock issue. Our understanding is still evolving. There might be fundamental aspects of quantum gravity or vacuum structure that we haven't grasped, which could present unforeseen obstacles or even show that large-scale extraction is impossible according to laws we don't yet know. We likely need further theoretical breakthroughs.
Okay, so the basic science and engineering are still massive hurdles. What about scaling up? Going from a lab experiment, if we even get that far, to powering the globe.
That leap is monumental. Demonstrating a tiny net energy gain in a lab is one thing. Scaling that up by many, many orders of magnitude to meet global energy demands. It's like comparing a small fluid dynamics experiment in a beaker to predicting the behavior of the entire ocean. The scaling challenges could be immense and introduce new problems.
And the cost,
Yeah.
building this infrastructure.
The initial cost of development, deployment, building ZPE generators, and perhaps those quantum batteries, it could be astronomical, at least initially. Who pays for it? How does it integrate with our existing energy grids, which might need a complete redesign?
It sounds like decades of work, trillions of dollars, even if the science works out perfectly.
Easily. And that brings us to the ethical dimensions. Access to potentially unlimited free energy. What does that do to us?
That's a deep question. What are some of the specific ethical concerns?
Well, the most obvious one, unfortunately, is weaponization. Any source of immense power can potentially be misused. Think about the dual-use nature of nuclear fission power plants and bombs. Could ZPE be weaponized in ways we can't even imagine yet?
It's a sobering thought. What else?
Economic and geopolitical disruption. Nations whose economies rely heavily on exporting fossil fuels could face collapse. That could lead to instability, conflict.
A transition would have to be managed incredibly carefully.
And what about the impact on human behavior? If energy becomes virtually free and limitless, does that lead to complacency? A lack of appreciation for resources? Does it change our fundamental values?
Interesting. Less striving, maybe?
Perhaps. And then there are questions of control and access. Who owns this technology? Could a few corporations or nations monopolize it, creating new forms of inequality? How do we ensure equitable distribution, especially to developing nations? The potential for creating new divides is very real.
So the technical challenges are matched, maybe even surpassed, by the societal and ethical ones.
They absolutely are. Harnessing ZPE isn't just an engineering problem, it's a profound challenge for humanity's wisdom and foresight.
So wrapping this up, this whole quest for zero-point energy, it feels like more than just finding a new power source. It seems to represent something fundamental about our drive to understand the universe and secure a sustainable future.
I think that's right. It taps into that deep human desire for knowledge, pushing the boundaries of what we think is possible. The challenges are, as we've discussed, truly formidable scientifically, technologically, ethically.
But the potential reward, it's hard to overstate.
Exactly. Human ingenuity has overcome massive obstacles before. The audacity of even imagining we could power our world from the energy of empty space is remarkable in itself.
If successful, it wouldn't just change our energy supply. It could reshape civilization, redefine our relationship with the planet, maybe even with the cosmos itself.
It really could. Which is why this needs a global collaborative effort. Scientists, engineers, policymakers, industry leaders, ethicists. Everyone needs to be involved in navigating this path.
And responsible development, equitable distribution, those have to be central from the beginning, not afterthoughts.
Absolutely critical. We need to learn from past technological revolutions and strive to manage this one, if it comes, with greater wisdom.
So for you listening, here's something to ponder. What would truly limitless clean energy unlock for human potential? Forget just keeping the lights on. Think bigger. What grand challenges could we tackle? What kind of future could we build if energy was no longer a fundamental constraint?
It's a future powered, quite literally, by the cosmos itself. It's a transformative vision, and while the journey is uncertain and incredibly complex, the destination, well, it's worth striving for.